Hello all, my name is John Noguera. I am the Chief Technology Officer at SigmaXL. Welcome to our webinar called What's New in SigmaXL version 8. This is the first of 3 webinars introducing the new features in SigmaXL version 8. Today we're going to cover the analysis of means charts, or the ANOM charts. The PowerPoint slide will be available. And another thing, most of what we're going to cover is also in the SigmaXL workbook, the PDF workbook that comes with the software. So when I reference data sets, those data sets are bundled with SigmaXL under sample data. And the examples that I'll be demonstrating are also all in the workbook as well. So our agenda for today, I mentioned to you this is the first of a 3-part series. So today we're going to introduce the ANOM charts, analysis of means charts, and then specifically the ANOM charts in SigmaXL. We'll look at normal, binomial proportions, and Poisson rates, both one-way and two-way. And within the two-way, we have main effects charts, slice charts, and then a yellow highlight recommending which of these two to interpret or to utilize. Also, non-parametric transformed ranks and variances in Levene robust variances. To begin with, we're going to make use of and refer to the book, The Analysis of Means by Nelson, Ludica, and Copeland. In particular, Dr. Ludica assisted us with the development of the ANOM charts. And in fact, we collaborated on extending what is called the slice chart. I'll talk more about that in a moment, but at the time the slice charts were developed just for normal and we extended them to binomial and Poisson. So that's a unique feature in SigmaXL.
What is an ANOM chart? It is a statistical procedure for troubleshooting industrial processes and analyzing the results of experimental designs with factors at fixed levels. It provides a graphical display of data. Ellis Ott developed the procedure in 1967 because he observed that non-statisticians had difficulty understanding the analysis of variance. And the analysis of means is easier for quality practitioners to use because it is like the extension of a control chart. This comes from the ASQ website. Also from the preface of the book, the goal of statistical data analysis is to use data to gain and communicate knowledge about processes and phenomena. Comparing means is often a part of the analysis for data arising both in experimental and observational studies. The analysis of means, ANOM, is an alternative procedure to the Anova for comparing means. It has the advantage of being much more intuitive and providing an easily understood graphical result. And it clearly indicates any means that are different from the overall mean, allowing an easy assessment of practical as well as statistical significance. The graphical result is easy for non-statisticians to understand and offers a clear advantage over Anova in that it sheds light on the nature of the differences among the populations.
Under graphical tools, analysis of means, you have these different ANOM charts, and we will be going through all of those. Also, we have within various statistical tests, we have added a checkbox. So under one-way Anova, you have here the option to display ANOM normal one-way chart. Under two-way Anova, you have the option to display ANOM normal two-way chart. Under Bartlett's test for equal variance, you can display ANOM variances chart. And under Levene's test, display ANOM Levene robust variances. Okay, so that just provides some additional flexibility. So either way, via the direct graphical menu or as a checkbox in your analysis, you can access the ANOM charts. Now, from the book, I just wanted to start. I'm not going to go into a lot of theory here. This is going to be very much a practical, hands-on webinar. But I do want to give you a flavor for what's going on. And essentially, the decision limits, I mentioned they look like a control chart, but they're not a control chart. A control chart has time as on the x-axis, whereas an anom chart has categorical levels on the x-axis. And the y-axis can be a mean, continuous normal mean, or the mean of a proportion, or a mean rate, or a variance, or a standard deviation. And the general formula is the grand average, or the overall average, plus a constant. And this is the part that Nelson, Ludica, Copeland, Ott, and others have worked to develop the critical values that are necessary for the anom charts to work properly. And that's this H critical value, which is derived from the multivariate t-distribution. You can think of this like basically like a t-statistic, but it's a multivariate t-statistic that's appropriate, and it takes into account not just the sample size, but the number of levels that you're working with, the number of categorical levels. Then you have the square root of the MSE, basically the standard dev, or the root mean square from the Anova. Then the square root of I minus 1 over n, and I being the number of levels. This actually looks very similar to confidence intervals for a mean based on the mean plus and minus t s over the square root of n. It's that same idea, but extended for multiple levels, for multiple comparisons. Now, this particular formula is for balanced data, and there are other critical values that are used if the data are unbalanced, and the software detects that and automatically applies the correct critical values. I'm not going to get into the details, but if you're interested, you can look into the book and the appendices of the SigmaXL workbook. This is the first example. Actually, let me just run that example in SigmaXL. So I have customer data, and I want to do an anom chart of overall satisfaction by customer type. So I will go to analysis of means, anom normal one way, use the entire data table, and I'll do overall satisfaction by customer type. The typical alpha level that we will use is 0.05 or 95% confidence level. Those H critical values adjust to ensure that the chart alpha level is 0.05 or 95% confidence level. And we'll go ahead and run that. And so this is our first anom chart. And we can immediately see, well, first of all, notice the moving limits. That's because the data are unbalanced. If the data were balanced, it would be a straight line. Much like in control charts, when you have unequal sample sizes, you have varying limits. It's the same concept here. If you have a larger sample size, then the interval or the uncertainty is smaller. And if you have a smaller sample size, then the limits are wider. It's the same idea as in a control chart with a varying sample size. And here we see that customer type 1 has a significantly low mean customer satisfaction, and here we see customer type 2 has a significantly high or higher mean satisfaction. That's, of course, as compared to the grand mean. So in an Anova, you're doing pairwise comparisons, and here in the anom, you're comparing against the grand mean or the overall average. And they really do complement each other. It's looking at the data from a different perspective, but the anom just makes it very easy to interpret. Okay, so that's the one way. Now I'm going to go back to the PowerPoint, and we'll look at two-way. In the two-way, we have what are called the main effects plots and the slice plots. And the main effects plots are similar to the one-way charts, but the difference is that the mean square error is derived from the two-way Anova. So it's actually fairly close. If I ran two separate one-way anom charts, it would be pretty close to the main effects, except for an adjustment because the mean squared error is used from the two-way Anova. Slice charts, however, are what we do with the slice charts is we compare the levels of one factor for each level of the other factor. So we'll see in a moment visually what the slice chart is all about, and it makes it really easy to interpret the effects, particularly in the presence of a strong interaction. That's when the slice charts are recommended and when they should be used. And in fact, we test the interaction and automatically recommend the main effects plot if the p-value is greater than 0.1, and if the p-value is less than 0.1, we highlight the slice chart. So you'll get that yellow highlight. Also, you have an option to adjust the Familywize error rate. That's a checkbox, so depending on the number of charts, we'll have an adjustment. It's important to realize that when we specify the alpha, that is the alpha for a given chart, for an individual chart. If we start creating multiple charts, then you might want to adjust for the fact that you have multiple charts, and that's a Bonferroni. So basically, if I have two charts, alpha will be divided by 2. So instead of 0.05, it'll be 0.025. Finally, on the two-way, we do allow unbalanced data, but we recommend that the data, if you're going to have unbalanced data, that it be just slightly unbalanced. We use data means rather than fitted means for simplicity in interpretation. Typically, a two-way anom comes from a designed experiment where you have balance. So for every combination of x1 and x2, you have an equal number of observations. So if there is a slight imbalance, let's say some missing observations, you're still going to be fine with the two-way. But a really large imbalance could be problematic, so we don't recommend that. Now we're going to look at an example from medical, and I have a question here about examples, areas of application, and wherever you would use an Anova, you can use an anom chart. So one-way Anova or two-way Anova, wherever you would use that, you can think to use the anom chart. So healthcare, manufacturing, transactional processes, chemical processes, anywhere that you're interested in testing for difference in means, the anom is applicable. And here we have a study, hemoglobin levels, and the control factors are therapy and drug. There are chemo and radiation and 3 different drugs, and we want to see the impact on hemoglobin level. So again, I'm going to run this example in SigmaXL. This particular example does not have a strong interaction or a significant interaction. Anom examples, hemoglobin. So you can see the therapy is X1. We have chemo and radiation. We have 3 drug types, and we have the hemoglobin level. So I go to graphical tools, analysis of means, anom normal two-way. The hemoglobin level is my Y of interest. I have therapy as X1, drug as X2. I will use an alpha level of 0.05, 95% confidence level. Right away you can see that the main effects plots are being highlighted, and the reason for that, if you scroll down, here are the interaction plots. And you can see the p-value of the interaction is 0.6. That is not significant. There is no significant interaction. The lines are essentially parallel or close to parallel, so there's no strong interaction. The software automatically takes that into account and highlights the main effects plot. We can see that for therapy, chemo produces a significantly higher hemoglobin level versus radiation. Radiation is significantly lower, and chemo is significantly higher than the overall mean. And drug 1 is not significant, drug type 2 is not significant, whereas drug type 3 has a significant effect on the hemoglobin level. I have a question here. What if the assumption of normality is violated? And there's two things. One is to keep in mind that central limit theorem applies. This is an analysis of means, so we're looking at distribution of averages. And because we're looking at distribution of averages, there's a good degree of robustness against the assumption of normality. But we also have the non-parametric version of the Anom chart, which we will talk about shortly. So when you have strong skewed data with small sample sizes, we recommend the non-parametric version of the Anom chart. So I'm going to go back now to the PowerPoint. And this is now an example of process yield. And in this example, notice the interaction p-value is very low. And you can see that visually the lines crossing on the interaction plot. So what is being recommended is the slice plot. And here what we have with the slice plot is with UV equals 1, so the factors are UV and monomer, and with UV equals 1, we are able to see the effect of monomer. Here, with UV equal 2, we can see the effect of monomer, but they look very different. Over here, when UV is equal to 1, monomer 1 results in a significantly low process yield, whereas if UV equals 2, it's a complete reversal. This is what the slice plot does. We hold constant one of the variables, so in this case UV equals 1, and then we look at the effect of monomer, and then we hold the UV at 2, and we look at monomer. So that's the slice plot. It's useful when there's a significant interaction, and so that's why it is highlighted if the p-value of the interaction is less than 0.1. Also, we have an example here where there's a slight imbalance in the data, and when you have a slight imbalance in the data, the results haven't changed, but you'll notice that the decision limits now vary slightly as a result of the imbalance or slight imbalance in the experimental data. So if there were some missing data in your experiment, this takes that into account. So I want to move on to binomial proportions and Poisson rates. The formulas are, again, very similar. Here, with binomial proportions and Poisson rates, we are using a normal approximation. So this is kind of like a p-chart and a u-chart in SPC. Those p-charts and u-charts are using a normal approximation. The binomial proportions uses the formula p bar 1 minus p bar, and the Poisson rates, the square root of u bar. So it looks very much like a p-chart and a u-chart with the critical values that are used for the normal Anom chart. If the sample sizes are not large enough, you will be given a warning message. If you see the warning message, then it's recommended that you, if possible, collect more data to get a larger sample size. And it's just at least an alert that there are some possible concerns about the normal approximation to the binomial or Poisson. Here's an example, school test scores. And in this particular case, we have different schools, and we're looking at test scores. Again, with the varying sample sizes, we have varying decision limits on the binomial proportions chart. And you'll notice that in this case, we're getting a warning message. It only indicates the first time of occurrence. It doesn't give you a warning message for every occurrence. But if, in this case, sample number 1 has n1 minus p equal to 2, so it's just cautioning you on the results. Typically, the results will still be valid, but it is something that you need to take into consideration when you're interpreting the Anom charts. Okay, so that's the binomial proportions one way, and then here's the Poisson rates one-way chart. So very similar, and in this case we have fixed decision limits, and we see belt speed as a significantly lower mean rate. And in this case, there were no warnings given, so we can conclude that the normal approximation to the Poisson is fine. Okay, so I wanted to include an example that showed the warning message and the varying limits, and then a clean example with the Poisson rates. So that's the one way. Now, in the two-way, this is where Dr. Ludica and I collaborated to extend the slice chart. Somebody asked the question, why do you call it a slice chart? Because Dr. Ludica called it that in his paper, in his original paper in the Journal of Quality Technology. And that paper is where he introduces the concept of Anom slicing. But essentially taking the normal concept and extending them to the binomial and the Poisson. And same idea, the yellow highlight automatically recommends main effects if the interaction is not significant, or the slice chart if the interaction is significant. Now, here's where it gets tricky, and this is where we're letting the software do the hard stuff. To get the interaction p-value for binomial proportions, you have to use logistic regression, and to get the interaction p-value for Poisson rates, you have to use Poisson regression. That's all done in the background. You don't see that. There's no report, logistic regression report. Simply the p-values are reported, the interaction p-values, and the yellow highlights are given. Also, again, with the one-way, if you have your sample sizes are too small, you're given a warning message. Here's an example, length of stay. This is length of stay in a treatment facility, and we have drug and treatment as the X category factors, and we have a strong interaction. So using the logistic regression, we get the interaction p-value, and so because of that, we have the slice charts, binomial proportion slice charts are being highlighted rather than the main effects plots. And again, it's interesting because you see here for drug A, treatment 3 is significant, whereas for drug B, there is no significant effect. And treatment 2 is just significant at the 0.05 level when drug is A. You can look at the interaction plots, but those are kind of hard to interpret, and you don't get the statistical significance on the interaction plots, on the regular, just the ordinary interaction plots. But when you look at the Anom charts, immediately you can see what's going on. And this is really the power of the slice chart in the presence of an interaction. Here's the ER visits data, Poisson rate, and in this case, the interaction is not significant. That interaction was based on Poisson regression, and therefore, since the interaction is not significant, the the main effects plots are being highlighted. Okay, so that's one example with a significant interaction and an example with no significant interaction, so the yellow highlight changes. In this particular example, I'm matching what's in the book, so I changed the alpha level to 0.01. In none of the examples in this particular tutorial are we adjusting the chart alpha for Familywize error rate? But that's actually, that's just something that if you want to do that, you can check that. And essentially what that'll do is that'll change the alpha levels. So in this case, it would be 0.005. Or if you started with 0.05, it would be 0.025. Now, earlier somebody asked, well, what if your data are non-normal? And I mentioned the central limit theorem. Central limit theorem kicks in, but sometimes you have strong skewness and you have small sample sizes, and it's just not going to work for, central limit theorem is not going to be adequate for the task. Essentially, anytime that you're thinking Kruskal-Wallis, think non-parametric transform ranks. It's not exactly the same as a Kruskal-Wallis. Kruskal-Wallis is an Anova on ranks, and this is a transformed rank. So the statistics are a little bit different, but the application is the same. In this particular case, I have an example where we have some data that comes from an exponential population, and we see clearly a significant effect. When x is 1, we have a significant positive effect, and when x is 3, we have a significantly low effect, or lower than the grand average. This data is actually quite small in sample size, and if you were to reanalyze the data just using anom normal one way, what you would get is it fails to detect any significant difference. So it was important in this particular case to use the non-parametric chart. So again, the guideline, whenever you're going to use a Kruskal-Wallis, you can use the non-parametric transformed ranks anom chart as a complement. It's not the exact same statistic, but it's a close complement. Variances. On the variances, we have, of course, the assumption of equal variances is important for an Anova. If the variances are not equal, you would use a Welch's Anova. But in addition, one of the things from a Six Sigma quality perspective is that if I have unequal variances, that's an opportunity for variance reduction. And that's something that a Bartlett's test and a Levine's test don't necessarily make it really clear. It tells you there's something going on, but it's not really obvious what is going on. And so much like the relationship between the Anova and the anom, here the anom variances chart is a complement to Bartlett and Levine's test. Bartlett's test is used when the data are normal, and Levine's is used when the data are non-normal. So we have the two types of anom charts. So this is an example using anom variances for delivery times, and nothing is significant, and that also matches the Bartlett's test. So we do have equal variances. You can choose between standard deviations and variances. That's just a display. You know, if you prefer to see your results in standard deviations, it'll display standard deviations. If you check variances, it will show as variances. And then the Levine robust variances, you're taking the observation minus the median, the absolute value. It's the absolute deviation from the median is what you're looking at. Same idea as the Levine's test, but now we're applying it in an anom chart. So it makes it robust to the assumption of normality. It's a measure of variability. And here in this particular example, we see customer type 1 has a significantly higher variability. Customer type 2 has significantly lower variability. Earlier we saw that customer type 2 had a significantly higher mean. Well, this is very important because what this tells us is that not only do they have a significantly higher mean, they're also, that's a higher mean SAT score, it's also less variable. So customer type 2 is doing something right. They're consistently getting a high level of customer satisfaction, and here in this case, responsiveness to calls. The variation in responsiveness to calls is significantly lower. Okay, so that's the Levine's anom chart. So we're looking at variances, robust variances, and if I actually just, I take the same data and I run this in a regular Anom chart, it fails to detect. So much like the earlier example where due to the non-normality, the charts aren't behaving properly, so we have the same issue here. Using the Anom-Levine chart is the appropriate chart when you have the non-normal data. And by way of illustration, I also have, here I show you the Bartlett's test versus the Levine's test on the responsiveness to calls. So as you can see, this tells you that the data are not normal and the p-value is not significant. Over here, the Levine's test tells you that the data are not normal, but the p-value is significant. So there is a statistically significant difference in variability. And the Anom chart, the Levine Anom chart, helps you to interpret that. Also new in version 8, which I'm going to talk about in the next webinar in 2 weeks, are these multiple comparison of variances. And that actually concludes the presentation. All right, so let me just have a look at some of these questions here. Okay, so Stephen asked about, not sure I fully appreciate the extra value that we're getting from Anom compared to Anova. And in some cases, it's obvious. The Anova pairwise comparisons show you that there's a difference between type 1 and type 2, but the Anom chart shows you differences from the grand mean. So it really is a different perspective. So in a way, it's a complement. Think of it as two different camera angles on your data. The Anom chart is the graphical view, makes it really simple, makes it really easy to interpret. It's harder to interpret the pairwise p-values, but the multiple comparison of means using Tukey's. The Anom also automatically takes into account the Familywize error rates. Also, please keep in mind we have here are the references, by the way. Oh, there's that. This is the paper, the JQT paper on Anom slicing, 2015 JQT. This is our poster session that we did together. And two more webinars coming up in 2 weeks and then 4 weeks. We have the multiple comparisons. There I'll talk about Tukey and Dunnett. The other multiple comparisons for the hypothesis testing, also chi-square tables and measures of association. And then in 4 weeks, we'll talk about the descriptive statistics, templates, and calculators that are new in SigmaXL version 8. So I want to thank everybody for their participation. Please do feel free, if you have further questions, to email them in. We're happy to answer, and I hope you find this software to be helpful and a valuable addition to your tool set. So thank you all very much for your participation.